to the closing panel today. And I started with a winemaker, and another gentleman is coming with a name of another winemaker from Pezinok. Marián Pavelka is the name of winemaker is Marián Pavelka, but now we are welcoming Marián Pavelka. And here with Mr. Pavelka, I need to say one important thing. 2 years ago, when I wasn't hosting this event, there were moments of heated discussions, but also silence. I looked at him. He changed all his presentation. He said, delete it. I have bad slides and the situation is changing, and let's put new slides. So I'm very curious what it's going to be. And we are talking about forest ecology and atmosphere and so on and so forth. And you are research employee from the Institute of Global Change Research. So let's get going.
Hello, thank you for invitation and possibility to have my presentation. I'm sorry to Mr. Dedeček. I was laughing during his presentation, but it wasn't because I didn't believe him, but it was my defending reaction not to have to cry. So I hope you will not be upset about my presentation. I have some more time because for 30 minutes I prepared a presentation of 2 hours. So let's start. So I am from the Institute of the Czech Globe, so which is a change institute, and we research atmosphere and how the climate was changing in the past, how it will change in the future. We also research the influence of the climate change on ecosystem and on society. And we used various kind of infrastructure of measuring stations. We are basically present in the entire Czech Republic. I am in charge of ecosystem stations, covering this basic types of ecosystems, and from those stations we took most of the data in my presentation. So together we have 250 stations, but now it's already 300. So I believe that we know a lot about the land in the Czech Republic, but also somewhere else. And the basis for our ecosystem stations is this covariation system. I'm not going to describe it because we don't have time. It measures 20 times per second the movement of air and concentration of gases, and then we know the flow of vapor and also from methane. So we know how much vapor we have from what ecosystem. This is some of the things we measure at our stations. So of course those are the woods very much with a lot of measuring facilities. And also it's like when the patient is in the hospital, has a lot of tubes in themselves, and doctors know everything about themselves. So in the last years we have been also present in the urban areas, and we have presented a lot of options with the roofs. Then we also have the distant research of the land, and therefore we have this and we can say a lot about the land just from one flight. we use hyperspectral analyzers, the thermal cameras, and radars. So we were able to create, there was even a video. This is a Brno, and this is, you can see what part of Brno is overheating and which one is heated and so on. So for Brno, we made this temperature map for summer and winter. This is for summer, including the details where we have our project Reurbanex at the high school at Olomoucka. Tomorrow we're gonna speak more about this. Now the topic of my presentation itself. I like the green. Maybe it will not look like that soon, but I really enjoy it. I like to go to woods with my girlfriend. We plant trees. However, the green cannot do everything that we expect and imagine. What we expect from the green, of course, it gives us the energy, we live from it, there is also carbon, it provides us the beauty and the aesthetic value, it has a lot of ecological functions, biodiversity, water, and so on. However, we will today speak about the a cooling function, because we speak about the adaptation for climate change. Sorry for the physicists who are here. However, I will speak about physics a bit. Cooling is the transfer of the heat or energy from the cooling object or cooled object to somewhere else. So we need to put the heat from the object that we are cooling somewhere else. So we do it by these three methods, and one of those is also change of the form, which is vaporizing, for example. So how much energy we need to get 1 liter of water in vapor? So I always show it like this to be aware. It means that for this we can need, let's say, 1 fridge with the refrigerator, or 1 chocolate, bar of chocolate. When the water evaporizes, it needs a lot of energy, which it takes from the environment, and therefore it cools this object that is cooled, cools themselves or itself and its environment as well. As I mentioned before, there is also another story what happens in the nature. We have the supply of energy. Every object that has higher temperature than 0K radiates electromagnetic radiation. So we impact, or the objects impact each other in radiation. So if I accept more energy than radiate, I will be heated, or vice versa, the other way around. So, or from the sun, we have the sun radiation, which heats the surfaces. Some of the energy reflects, some changes into so-called obvious heat, which heats our our air and the environment. This is what we can measure with the thermometer. Latent heat is evaporated. Part is goes into soil during the day, and during the night it goes back. And also certain amount of energy leaves by the infrared radiation. So all of this basically heats the atmosphere, which brings us the heat back. And this is exactly greenhouse effect as we know it. So this happens on the field. However, it also happens in the wood, which includes water. So the question is, what is the energy flow? how much energy leaves in what, through what way. This is crucial, so to say. If you check online, maybe you know these kind of schemes, and you will see there quite often that from the from the land without water, there is more than half of the energy leaving this, and the evaporation is only 1 to 20%. If there is sufficient moisture and water, there is evaporation of 70 to 80%, which is great. If it works like this, we get rid of the energy very well. However, the question is if this is really the reality. So this is the scheme from the internet, and it is very popular in various with various values, and from our ecosystem stations, but also on various types of roofs. We checked these figures and we also measured this. So when we put into ratio these two heats, this obvious heat as our wind is heated, and the latent heat, how much energy is going away in evaporation, we get the Bowen's ratio. And here in the land without water, it's 3 to 7, which means 3 to 1 or up to 7 to 1. There is it's the ratio of the obvious heat to the latent heat. The land with a lot of water, it's 1 to 7, up to 1 to 17. In favor of the water. We checked this as well, these values, and we found it as well. We found the same thing, that this moist woods, this forest with moisture or with water, it also has cooling effect. So how much did we find of it? Within 7 years, we found it at 10 half an hours. So it seems that it's not the typical conduct of this land. So it works. I mean, the scheme is true, it's not false. However, it only selects the peak values. And and this happened shortly after the rain. So we have, this was some heavier rain, this was some less heavy, and this is the yellow line is after sun. So this is evaporation of the rain, and water is retained on the surface of vegetation, and we had similar values. So in the summer, the nature can do that. However, it's very precious, it's very rare. When we check this Bowen ratio again, so this ratio between the obvious and latent heat, this brown line shows when these two heats are equal. When we have the same amount of heat leaving by the evaporation and the obvious heat. So this is the wet environment, and we see that in the wet environment it can conduct as this, but how often? This is not even typical conduct or behavior even for the land with a high amount of water, and this is not even typical. And where can we get a more amount of water? So this, what we see above it, is also the area with higher volume of water. And if we check some different ecosystem, let's say this is the field. Field is well, with less amount of water. And we see that even this field behaves sometimes as this moist land and sometimes as the dry. But those are rather selected peak values. So It's not a typical behavior of the land. Okay, this is Lanzhot. This is very much water, in this land there is a lot of water, what it looks like. So this is cooling, so we are below 1, but in the summer afternoon, where do we have some significant cooling in this blue area? Where is this huge cooling? It's not here. It's 10 half an hours within 7 years. This is the pine wood at Bílý Kříž. There is still sufficient amount of water, but we are getting here to a slightly different situation, because here we are in the summer day hours around noon, very often above 1, which means that the wood takes this energy and it basically heats the environment and produces much more obvious heat, so it doesn't cool. If we check this pine wood Rajet Jestřebí, which is not existent anymore, there is nothing there in this land. But this wood, I don't know, I don't see this as a cooling effect of the land. This wood rather heats the atmosphere. So, do we still believe this scheme? I do not anymore. For a few years. It is true, but only in very specific situations, and it's definitely not ordinary behavior of the system or the ecosystem. So those are the values we measured for our or at our stations. So we have 4 components of balance measuring. So this is what it looks like according to these colorful stripes. We see that this behavior throughout the year, those are the average values throughout the year. So summer, autumn, winter, spring, day and night. So if we count it all together, this flows looks like this. And by this obvious hit, we radiate here 17 in the field, and in the wood 23, and in the field 45% with evaporation, and 53 in the wood with evaporation. So it's definitely not 1 to 16 ratio. It's the ratio 1 to 2 or 1 to half or 1 to 2.3. So sometimes in the field it's even better. So if we check the average of summer days, so 3 summer months together, day and night, what it looks like, well, we have the ratio 1 to 1.6 and 1 to 2.2, field and wood. So the twice as much energy of the energy leaves with the evaporation, but not the 10 times or 16 times. And this is the wood close to the river. And if we check the summer afternoon values of these radiation days with a lot of sunlight, we have this ratio 1 to 1.2 and 1 to 1.4, so field and the wood. So the green area cools, but not as much as we thought. And what I would like to emphasize are those flows of invisible infrared energy. And if you check how much energy is leaving, you see that through infrared radiation there is a huge amount of energy. So This energy from the latent heat, this evaporation, is rising up, this water steam, it condensates and then the clouds are created, whereas the energy, the entire energy is released and it stays in the atmosphere, it remains in the atmosphere and it shines back to us with the greenhouse effect. This infrared energy heats us like this. This obvious heat is something which we feel. The atmosphere is warmer, so it radiates on us more. And the only way how to get rid of this energy efficiently is the reflection, because what is reflected 75 to 80% of this reflected energy leaves to the universe. So what this means, to make the land lighter, to make the cities lighter, to give more light. Therefore, this is how we can get rid of this energy. This infrared energy has one disadvantage, that it heats up the atmosphere, and there is basically the basis of the greenhouse effect. 80% of the energy of the infrared energy, which is radiated by the surface, is caught by the one layer of the atmosphere up to certain height. What would you say? Where the most of the greenhouse effect is occurring? Who thinks it's more than 2 kilometers? It's higher than 2 kilometers. Who thinks that it's higher than 1 kilometer? Atmosphere has 100 kilometers approximately. 80% of this energy is caught up to 300 meters. So the greenhouse effect is happening here, very low. It's not in the universe, or it's not on the verge of the atmosphere, it's just here. So this is not the correct scheme. If we have a look at the average summer day and the flows of energies in the pine wood in Bílý Kříž, where there is sufficient amount of rainfall, so in the average time and average summer day we have more obvious heat. This is where it is hottest. This is when we need the wood to be cooling the most, but it doesn't. Why? Because it cannot evaporate more water. It's just not possible. I was speaking about this reflection. We use albedo. It's the amount of the reflected global radiation divided by the falling global radiation. So we have here the values for various materials. So most of the ecosystem we have there, like the pine, the field, the meadow, the wetlands, and you can see that when we have the highest values is given by the light and by the color. So these pine woods are not very cooling. What about the cities and the materials, how they are cooling us? Those are the values that we have from our measures, and this table basically says that it is measured for summer day with the air temperature 30 degrees, which is not extreme. Then the sunlight 800 watt for square kilometers, which is nice weather but nothing extreme. Then we have this greenhouse effect, and the materials are heated. The least heated is the grass, More heated is the white roof. Why? Because it reflects a lot of shortwave energy. Then more heated is the dry grass. For example, the green roof that we do not water frequently, and we do not take care of it because it's expensive or we don't like it. That's just ruined investment. And then we have cheap. Then we have the cheap roof, and it heats the most. So when we spoke about the energy flows, this is the heat duty of these heat materials. This is based on albedo and ability or disability to evaporate water. So this is the simple cheap roof, which is already dry, and there is no evaporation basically, and this heat duty for dark materials. Are there architects here? No, please do not do black roofs, please. This does not reflect anything. The white roof reflects something, but what was surprising are these extensive, not very well made green roofs. And if we see how much heat goes to the air, which is direct heating, I'm sorry, but we have it that this non-cracking simple roof heats the air more than the black. It looks like nonsense, but the reason is that when the black roof is heated to higher temperature, it radiates more, it loses more energy. This simple roof is also heated, but it radiates less. And it has better contact with the air because it has a lean surface. And this is what the green does in general. But this simple, these are, sorry, different, these are more extreme, more peak values, not extremes. So we have here the roofs, 73 degrees for the dark roofs, and we have this 52 for the extensive green. Then we have intense green roof, not watered, for 35 degrees. Okay. Let's go back to this transpiration, so this storage of evaporated water. So with standard trees and corn and grass, these openings are open. Then there is photosynthesis because the plant accepts CO2. Then we have the dry plants, succulents, and they survive because they open for the night and they lose the minimum amount of water. So, and they catch the CO2 to certain chemical bonds, and they do this photosynthesis during the day when their openings are closed and they do not lose water. It's a great adaptation thanks to which they survive drought. However, during the day, they cannot cool down by transpiration. I'm sorry to the translators, but this is an additional slide, but I have it here in Latin in some other languages. So this is the transpiration. So this is through the evaporation through the plant. So if the roof has a very high quality plant, there is some retention from the soil, but it's much lower. Then, does it even make sense to have green in the city after what I said? Of course it has. I said I love green in all forms. Why? Because it doesn't heat that much that it accumulates heat for the night. And this heat island of the cities is much bigger during the night. So, and as it doesn't overheat as much, and it means that we have less radiation, and our heat that we feel is much better. We both know that it's better to put your foot on the grass than on the concrete. It's nothing new. And what is the best is that it can provide shadow, and this is something which we cannot really enjoy with grass, but we can maybe not even with bushes, maybe only if we crawl, but especially we can enjoy shadows under trees. And this is this AC function. We can also create these artificial shadows, let's say some sun umbrellas, then some cold drinks. However, this roof can be heated up to 50 degrees, so we can hide against the sun or in front of the sun, but we are under the radiator, so it's not ideal. And the feeling from this shadow is completely different than from the tree. And this is the huge amount of water in the tree, and therefore it cools down and we have a better, more comfortable shadow. Sorry, can you move me on because it doesn't work? Thank you. So if it's this dense tree, this is the Auburn close to our institute, sitting on this bank is really nice also on the heated day. Why? I call it the effect of multi-layered shadow. They also use it on the James Webb telescope already, which is bearing infrared camera for the distant part of the universe. And it must be in a cool environment. And how they did it? They put 5 layers of very thin metal foil which reflects the radiation. It heats a bit, and then another energy is transferred to another layer, but most of it goes away, and step by step it basically cools down this energy up to zero, almost to zero. So in the tree it's not this strong, but the similar principle is there. So if we see this tree on the thermal camera, we see that this temperature is more than 35 degrees. This is an oak on our garden. If we move here, this is the view from the bottom. So these are the leaves if they were only in one layer, so it would be almost the same as artificial shadow. But as the tree is big with more layers, it basically shadows itself and brings the shadow to us. So why I mention this? Because we should appreciate big old trees with huge crowns. So if we, for this big tree, plant 10 or 15 new trees, we will not be cooled down by their shadows, maybe our children, but not us. So the conclusion of my presentation is the cooling with evaporation is overestimated when it comes to green. And I showed you this scheme, which maybe if you use it, stop it, because it's not correct. Then also the cooling depends on the availability of water. If we don't have water, we cannot expect much cooling. This scheme completely forgot about the infrared energy which lives there. albedo, so light surfaces. If you are architects and if you can speak about, or if you have can affect the face of the cities always make it lighter and lighter. So if we had all white roofs, maybe we could imitate icebergs or glaciers. Let's say, do not use dark gray or black colors in the city. So the dark surfaces absorb much more than of sun radiation than the light ones. Green extensive roofs achieve surprisingly high temperatures. It is not a very convenient adaptation, so it's nice to look at it, it's a good impression, but it's not that efficient as we thought. And huge trees, so let's protect them, let's defend them, let's have big trees, let's enjoy the green, but be aware that it has its needs and it has its limits. We cannot expect from the green areas something which they are not physiologically able to fulfill. Thank you for your attention. Thank you very much. It wasn't that depressive. I think we have started a new trend. Mr. Masaryk, professor, started with the good jokes and we are continuing. I took something from this. I have a black roof on my house and I will have to change it, so congratulate to myself. But when speaking about watering the garden, I always water also, or I spritz the water also on my roof. And when people ask me why I waste water on the roof, I cool down. So, and during the lunch, you can give me some more tips and tricks. So, and when speaking about lunch, I am already hungry in my stomach. Let's move not to coffee break but to lunch break, and we will continue with our presentation. But before that, please be punctual and please leave your headsets in this room. Do not take it out of this room. This beautiful lady is waiting for your registration to win the car for the weekend, and also we will have a new dots competition, so the prizes are nice, there are a lot of them, interesting ones. Also these beautiful green things from our partners, and I think most of you who are here as our partners, you will hand the prizes in person. So there is at the entrance there is this white bowl, there is a pencil and a piece of paper, so write out your name, your company or where you are from, and we will have the we will maybe pick you up and you will win a prize. So we will continue in the presentations after lunch. I hope that the journalists will not be upset about me, that the journalists just come here, have lunch and they leave. So I hope that you will also stay with us after the lunch. So thank you very much and enjoy your meal. Thank you.